Good afternoon, everyone. Welcome to session of electric vehicle use and behavior at the BTR conference. I'm Mohammad Miraji Naqi, Assistant Professor in Illinois Institute of Technology. I'm honored to serve as the chair for this session. Today, we have outstanding lineup of presenters from different states of the United States and also United Kingdom. We will explore a wide range of important topics on electric vehicle use and behavior. We will begin by examining whether EVs pose greater risk to pedestrians compared to internal combustion engine vehicles. Then we look into how EV drivers behave during emergency evacuations, particularly driving route and charging decisions. We have other discussions, presentation on potential of vehicle-to-home charging to reduce cost and emission, the vulnerability of EV charging infrastructure during hazardous events, spatial patterns of EV accessibility across the United States, and effect of e-bike rebate program on travel behavior. So these studies, they are really important. They would help us on understanding how EV will reshape mobility, infrastructure planning, and user behavior. To keep within the time, the presentations, each presenter will have 15 minutes for presentation, 5 minutes for Q&A. I kindly ask that each presenter stay within their allotted time so that we can ensure the smooth session and we have time also for discussion. So without wasting any time, let's welcome our first speaker, Zia, on his work on are EVs more dangerous for pedestrians than ICEVs. Thank you.
Okay, thanks, Mohammed. Can you hear me?
Yes, I can.
And slides are all right? Can see my slides?
Yes, I can see.
Oh, okay, all right. Okay, good evening from the UK, actually. I think it's afternoon in the US now. So I'm Zia Wadood. I'm a professor of mobility and energy future at the Institute for Transport Studies at the University of Leeds. And today I'll be talking on whether EVs are more dangerous for pedestrians than ICEVs or internal combustion engine vehicles. Now, those of us who work especially in the mobility and energy nexus, we work on decarbonization. We know that vehicle electrification is one of the biggest or most important paths towards decarbonizing transport sector. But also, it is now important, and various countries have gone full steam ahead with EVs nowadays. But also because of that, I think it is becoming important to understand the wider implications of electrification of our transport system. So yes, electric vehicles reduce carbon emissions, probably reduce local air pollutants as well. But we have, as transport professionals also, we have broader sustainable mobility goals, right? And I've done a recent commentary piece, not research, commentary piece in a journal recently on whether EVs can deliver sustainable mobility. And we wanted to look at like 7 aspects of sustainable mobility and how EVs affect those achievement of those goals or not achievement. And EVs can be beneficial for many of those. And one area we found at that time was quite, there wasn't enough information is on the goal that all of us want to reduce traffic deaths and injuries, right, from road transportation. And around the same time when I was doing this, there was this headline news item in The Guardian that electric cars are more likely to hit pedestrians than petrol vehicles. And that obviously struck me like, wait, we are reducing one type of risk by reducing air pollution and greenhouse gas emissions. But if EVs are really more risky than electric cars, that is really worrying. So that's when we started this piece of work. This has been sensationalized. The study itself from our colleagues was not just about electric vehicles, they were more about hybrid electric vehicles. There were very few battery electric vehicles at that time, but I wouldn't get into that detail now. So what we wanted to look into is actually whether electric vehicles, battery electric vehicles and or hybrid electric vehicles could have a different risk profile compared to ICEVs for pedestrians especially. And there are reasons for different risk. For example, the first one is, and we know quite a bit about this already, that EVs and both battery electric vehicles and hybrid electric vehicles are significantly quieter than regular ICEVs. And especially for pedestrians and visually impaired people, that can pose a huge risk of collision. So the risk of collision could be higher because these are simply quieter vehicles. Even after the addition of those acoustic vehicle alert system or AVAS, electric vehicles and new hybrid electric vehicles are still significantly quieter. The second risk factor is that electric vehicles are substantially heavier. These are two Golf vehicles of similar type. The left one is two Volkswagen vehicles. The left one is Volkswagen Golf, which is an ICEV. The right one is a Volkswagen ID3. I don't know if you get these vehicles in the US yet, but they're quite popular in Europe. And you can see that the ID3 is almost 43% heavier compared to the Golf. And what it means is that if a collision happens, then there's a higher risk of a severe injury to the pedestrian or to the vulnerable road users who are hit. So the two are different things. One is this increases the risk of collision or collision rate. And the second one is if a collision happens, this increases the potential for a severe injury. Mitigating these to some extent is probably that EVs, especially the new battery electric vehicles, they probably have more technology, more driving assistance systems. I read in newspapers several years ago that because they were more expensive vehicles, manufacturers were putting more and more other type of technology as well to entice users or consumers. And these emergency braking system or pre-collision alert, other driving assistance system, they may reduce the risk of a collision, but also they may cushion the impact of a collision, which means that EVs or hybrid electric vehicles could be less risky in case of a collision compared to ICEVs. So our research questions are, one, whether pedestrians' risk of collision with EVs is larger than that with ICEVs. That's the quietness thing. And the second one is, in case of a collision, are pedestrians likely to be more severely injured if the hitting vehicle is an EV, HEV, instead of an ICEV? And this is more about the injury severity, the heavier weight thing. So the way we do it is in terms of methods. The first one, we use simple aggregate casualty rates, which is number of pedestrian casualties hit by either battery electric vehicles or hybrid electric vehicles or ICEVs, and the VMT, the exposure, which is billion miles of EV travel, billion miles of hybrid electric vehicle travel, etc. And we use what is known as casualty rate ratios in epidemiology, which is basically the casualty rate of EV divided by casualty rate of ICEV. And if this casualty rate ratio is equal to 1, then you can say that these are equal. The risk is similar for both type of vehicles. And depending on whether it's greater than or less than 1, you can say whether one is more risky than the other one. And for the second, this is using aggregate tables, okay? And the second one is, for the second one, we use actually the micro data set, which is we have data for every casualty for the years that we will be working on. And we run a binary logic regression to understand the injury severity and various factors that may affect injury severity. Our core data set is Stats 19 of Great Britain. That is similar to US's, I think, FARS. No, sorry, FARS is fatality only. The other one, CRSS, right? So it's more similar to CRSS, which records all the data. But unlike CRSS, which is, I think, 10 or 20% sample, this is all collision data. And we use US Department for Transport data for VMT and specialized another index for VMT for electric vehicles. And we are interested only in pedestrian casualties at this point in time. So these are the casualty statistics. As can be expected over time. This is reducing with obviously a huge fall during COVID. The dashed one is the overall. The red one is for ICEVs. The blue one is hybrid electric vehicles going up because the number of vehicles are going up. And the green one is electric vehicles, which have basically just started picking up rather in the last 5 years. This is the number of vehicles, still a huge vehicle fleet is ICEVs, electric vehicles, and hybrid electric vehicles are just getting some traction. Please note that there are two scales in the casualty one. The left one is for all and ICEVs. The right one is for electric vehicles and hybrid electric vehicles. And then the variable that we use for exposure for casualty rates is VMT, not vehicle number. And again, this kind of, as expected, VMT is falling during the COVID and started recovering. It has fallen for hybrid vehicle as well, but then started going up rapidly. And electric vehicles, obviously, around from 2019, it has started going up very, very rapidly. And this gets us to, so this casualty divided by VMT is basically our casualty ratio. As you can see, the early years, the casualty rates were quite high for both EVs and ICEVs compared, EVs and hybrid electric vehicles compared to ICEVs and averages. And also there's a bit of kind of instability in early, especially for EVs, you can see very high. And one of the reasons I think is because the VMT for EVs back in 2014, 2015, there could be some errors in there, and those errors get multiplied proportionately, right? Because we are talking about very small number, and a few numbers here and there can change things massively, which is not the case for ICEVs. But around from 2019, when the number of electric vehicles have started growing rapidly, but also the AVAS system has started, was being mandated in the UK. You can see that the casualty rates have started falling, both for electric vehicles and hybrid electric vehicles. And it looks like BEVs have kind of fallen to the same as ICEV, whereas hybrid vehicles, it still hasn't fallen as much. And that is something that is interesting. So these are the kind of the statistical analyses. We are primarily interested in 2019 to 2023 because that's when we have more electric vehicles in the system. Some of the early numbers, I'm not sure how reliable they are. These are the rates that you have seen figures. These are the two tables that we are interested in. The casualty rate ratio between EV and ICEV, as you can see, both for individual years and as a whole, they are statistically not different from one. For our 2019-2023 aggregated data set, we see that for Poisson and for negative binomial, we have used both both distribution assumptions. They are statistically not different from one. What it means is that the risk of a collision, risk of pedestrian collision with an electric vehicle is statistically not different from ICEV once we have considered the vehicle miles travel of those vehicles. The case is not the same for hybrid electric vehicles. Remember, the hybrid electric vehicles were the driving factor for the Guardian article that I have shown that used data from 6-7 years ago. But even recent data, it does show that hybrid electric vehicles are still riskier for pedestrian collision. And that is intriguing, but we think there are a few reasons. And the first one, the main one, is in the UK, hybrid electric vehicles are used a lot for private hire vehicles, the Uber type vehicles. And these vehicles, there are two things that's special for these vehicles. Number one is these vehicles drive a lot in urban areas, in city centers where there are a lot of pedestrians. And that means the exposure is much higher. And that is probably the reason why, despite after even AVAS, while they are falling, they're still significantly higher than the risk for pedestrian ICEV collisions. I'm happy to hear if you have any other views for hybrid electric vehicles, because this is really intriguing for us. The second one we wanted to look at is the injury severity regression. That's our research question 2. And this is the one where we have used microdata, casualty level, individual casualty level data. And our dependent variable is injury severity. Slight injury is 0, and severe or fatal injury, we have grouped them together, and that is 1. We have run a binary logistic model, and we have tried binary probit as well. And we have tried to control for as many of the factors that we have access to, whether it's not just EV, HEV, but whether it's an SUV, speed, weather, road surface, junction types, light conditions, vehicle maneuver type, characteristics of driver, age, gender, characteristics of the casualty, age, gender, etc. And of course, this is a big regression table. I'm not going to show all of you. The key one I wanted to show is the role of EV and HEV. By EV, I mean BEV, of course. Again, so let's start with the HEV. Hybrid electric vehicles, we see that the risk of a more severe injury of a pedestrian, if it is hit by a hybrid electric vehicle, is statistically less than the risk for ICEV. That means that they are safer. In case a collision happens, the likelihood of severe or fatal injury is less for hybrid electric vehicles. That is possibly because these vehicles have, again, better technology like driving assistance systems, because they are also quite expensive. But that hypothesis doesn't stand for EVs, because you can see that they are not safer. And our conjecture is that EVs would have been safer as well, because EVs have even better technology. EVs are a much newer fleet compared to HEVs. But EVs are significantly heavier compared to HEVs and ICEVs. So the benefits of those additional technology or driving assistance system, emergency braking system, that would have made EVs safer or less harmful for the pedestrian is countered by the heavier weight of the electric vehicles. So that is our conclusion on this area. Very briefly, I wouldn't go too much onto the role of AVAS because I'm running out of time. But what we can see that since the introduction of AVAS, at least graphically, you can see that the collision rates have started falling as well. So to conclude, are pedestrians' risk of collision with EVs larger than that with ICEVs? For battery electric vehicles, no. There's a similar risk for pedestrians as ICEVs. For hybrid electric vehicles, there are still higher risk for pedestrians. for reasons that I have mentioned, that a lot of those vehicles are used as taxis, which run a lot in urban areas. For research question 2, in case of a collision, are pedestrians likely to be more severely injured if the hitting vehicle is an EV instead of an ICEV? For battery electric vehicles, no, similar likelihood of severe or fatal injuries as ICEVs. However, hybrid electric vehicles are less harmful in case a collision occurs. I wouldn't get too much into that. I think I'm running out of time. And thank you.
Thank you, Zia. So we have time for one question. No question.
Okay.
So I have one question for you. So what's your recommendation? So you mentioned that the hybrid electric vehicles, they have a higher likelihood of collision because one of the reasons is because of using them in the ride-hailing companies. But what's your suggestion?
I do not have any particular suggestion because there isn't any technology fix of that, because new hybrid electric vehicles also will have the AVS, right? So the vehicle alert system is there, the acoustic alert system will be there. So I think it is less of the vehicle problem and more of where the vehicles are driven, right? So even if you replace, so my hunch is that even if you replace, say, all the hybrid electric vehicles with electric vehicles, then I think the collisions with electric vehicles and pedestrians will be higher in that case, simply because they're happening closer to people. So it's less about the vehicles themselves, I think, more about where they are driven now. Yeah.
And we have one more question. If you control for ADS technology, do you think the result would be different?
That is, I would love to do that, and I think I do have. So that was one of my future questions, evidence of that. I would love to control for that. Unfortunately, I do not have access to that data. And yes, some of the results might be different, yes. Because a lot of it, the safety for EVs, I think, is driven by the availability of better technology. I cannot prove it. That's a conjecture at this point in time. But yes.
Thank you, Zia. So our next speaker is Denisa from UIUC on the evacuation behaviors for electric vehicle drivers, routing and charging choice experiments.
Okay, hello everyone. My name is Denisa Purba. I'm from University of Illinois Urbana-Champaign, and today I would like to share my recent work on evacuation behavior of electric vehicles drivers, route and charging choice experiments. Electric vehicles, or EVs, adoption is rising to support transportation decarbonizations. There are a lot of study has been focused on EV transportation planning in both habitual and emergency operations. However, evacuation behavior analysis of electric vehicles drivers remains limited in evacuation behavior field and also in EV literatures. So evacuation decisions depends on the individual and household decision-making processes and characteristics. The existing literature often focus on the key evacuation questions, such as how people whether people choose to evacuate or not, where should they evacuate, when should they evacuate, and how they evacuate. Now, when we introduce electric vehicles to the evacuation decision of these drivers might also be impacted by the vehicle's technological characteristic. These may introduce new questions such as which evacuation route or corridor to choose, Can I charge my vehicles during evacuations? Where should I charge, and how many charging stops should I make before reaching the destinations? So in this study, we aim to identify the effect of various vehicle specifications and charging station characteristics on evacuation decisions, especially the EV driver's route and charging choices. Here are our overall frameworks. We develop a web-based stated preference survey that incorporates 5 key attributes groups, which is the evacuation characteristics. We consider a mandatory order and several evacuation distance, road characteristics, the vehicle's characteristic itself for the EVs like battery capacity, SOC at origin and destinations, charging station characteristic, and socio-demographics. And then we will develop logic-based models to quantify decision behaviors and apply the behavioral models that we fitted to the evacuation road plannings using stochastic user equilibrium models. Here are the design for our stated preference survey. We use Engine to design the efficient choice set and implement our survey using Qualtrics. In our survey, there are 3 parts. The first part is the identifications of the socio-demographic and vehicle characteristic questions. The second part is the evacuation route and charging choice experiment. And the last part is the evacuation attitudes. For the evacuation route and charging choice experiments, each participant is situated to the evacuation mandatory order, and they need to evacuate using electric vehicles. There are 2 mandatory evacuation scenarios that we consider here. First is the 100 miles short distance evacuation scenario. The second one is the long distance, about 300 miles evacuation scenario. We consider the short distance here to evaluate how EV evacuees making road and charging decisions when they still can complete the evacuation without charging. And its respondents will need to choose the 6 roads alternative. 3 of them, 3 roads is without charging, and 3 roads options is with charging. For the long distance cases, we want to use these cases to evaluate EV evacuees and on how they make road choices when charging is required to complete the evacuations. And its choice task, we presented 3 roads alternative with charging stations along the evacuations process. We conducted the survey last year in 2024 from July 26 to September 30. We collected respondents about 255, and after cleaning and verification, we have about 157, and 81 of them are EV drivers. And from 157 participants, we obtained about 1,884 choice observations. Here are the examples of the scenarios in our surveys. The left side here is the short distance mandatory evacuation that is illustrated in Chicago networks, and the long distance evacuation is illustrated using Florida evacuation corridors. For the discrete choice modeling, we use a simple logit model structures. For the short distance, we will evaluate 6 options, which is 3 roads without charging and 3 roads with charging. And we consider 2 types of logit models, which is multinomial MNL and also nested logits NL models. For the long distance evacuation scenario, we will evaluate 3 alternative choice set, which is the roads with charging, and we will fit it with multinomial logit models. Here are the fitted models that we have for the short distance evacuation road and charging choice analysis. We developed 2 MNL models and 1 NL models. Some key insights that we found here. First is that the EV evacuees are more sensitive with the travel time and charging time. And the evacuation route with chargings in short distance cases is not preferable. This is very expected because in short distance scenario, they have options to not charge at all. And from our fitted models, we found that choosing a route with charging is not preferable. We also find that EV evacuees prefer roads with high SOC or the state of charge at their destinations. Then we analyzed interactions between SOC origins, SOC destination, and also total charging stations in the evacuations. The interaction between SOC origin and SOC destinations for the short distance cases is substitutable. It means that when the EV evacuees begin with a low state of charge at their origins, they are more likely to choose routes and make charging decisions to ensure high SOC at the destinations. The interaction between SOC origin and charging stations, total charging stations in evacuations is diminishing. It means that even when the EV evacuees begin the evacuation with low SOC at origin, they're still less likely to choose routes that have more frequent charging stops throughout the evacuations. And this one is the long-distance evacuation routes and charging choice analysis result. We fit it with two models, two MNL models. Some key insights that we found here is that under long-distance evacuations, queuing time become more sensitive to them. And then they also still prefer roads that can ensure high SOC at destinations. And when we evaluate the interaction between SOC origin and SOC destination, we found that it's quite different from the short distance. In short distance, previously, the interaction is substitutional, but here it's complementary. So it shows that under long distance evacuations, even though that the EVs evacuees can start evacuating with high SOC origins, in the end, they're still more likely to choose routes and make charging decisions to maintain their high SOC at destinations. For the interactions between SOC origin and charging stations, it is still the same, it's diminishing. In the last part of the survey, we asked about their evacuation attitudes. In this part, we asked the respondent about their preferred vehicles type for evacuations. So the non-EV owners, 85.5% of them highly prefer gasoline vehicles for evacuations. This low preference might indicate there is unfamiliarity about the vehicle's technology or concern on charging during evacuation among non-EV owners. For the EV owners, we found a mixed preference. 44.4% of them prefer EVs for evacuations, but 55.6% of them still favor gasoline vehicles. So this mixed preference might suggest some lingering concern, either due to the vehicle's performance or the charging's availability during evacuations, and also there might be also their unfamiliarity about the evacuation order. Lastly, we also asked them to rank the important attributes that help them to kind of like making the road choice and charging choices. And here are the ranks plots there. We found that both EV owners and non-EV owners share similar decision-making priorities among the evacuation attributes regarding the road and charging choices. However, the non-EV owners seems more focused on attributes that represent the vehicle's characteristics, the EV characteristic itself, and also the evacuation performance. These seems prioritize the evacuation travel time, SOC at origin and destination, and number of charging stations along the evacuations. For the EV owners, they tend to focus more on the EV characteristics and charging infrastructures. They put a higher priority towards vehicles' driving range, charging location along the road, and also charging time. So this ranking kind of like show us that EV owners have higher familiarity about vehicles technology and charging process and have higher awareness about the importance of charging infrastructures during evacuations to complete their trip. We also try to kind of like implement our evacuation behavior models to the evacuation road planning. we trying to implement it into two cases. We use Chicago during flooding evacuations cases to represent the short distance evacuations, and then South Florida during hurricane evacuations to represent the large scale, the long distance evacuations. And we simulate the evacuations throughout these two networks using stochastic user equilibrium with the fitted behavior models that I presented earlier. Here are the EV evacuation routing plan for Chicago floodings. Through the modeling, we can kind of like track the road choice and also where's the locations they charge and how many what is the energy demand required for each stations in the networks. Here on the left side is the EV evacuees is when all of the EV evacuees start with the full battery in the network. On the right side is some of EVs start with a near empty battery. We found here from the left when all of the EV can start with a full battery of charge, there is no EV evacuee that needs to charge in this case. This is expected because this is short distance models, and from our behavior models, we also see that there is less preference to complete to charge in short distance evacuations. However, when they start with a very low associate origins, we noticed that about 220 EV evacuees choose to charge to maintain again their SOC destinations, because in our model it shows that the SOC at destinations have a very high preference, and then the interaction between SOC origin and SOC destination is also substitutional. So if it's low here, then they want to achieve higher SOC at destination. That's why we can see that 220 EV decided to charge in our models. We also tested in the EV evacuation routing plan for South Florida hurricanes evacuations. Here, because of the larger networks, we noticed there are 33 EVs needs to charge under a full battery SOC origin 100%. But when some of the EV evacuees start with low SOC at the origin, we notice again 659 EVs evacuees choose to charge. And this is again as expected through our models that to maintain the SOC at destinations. So as a summary of findings about these works, we found that the evacuation distance impact the evacuation route and charging decisions slightly different. So for the short distance evacuations, when charging is unnecessary, we found that the EV evacuees are more sensitive to travel and charging time. They also prefer not to charge. And we noticed that the relationship between SOC at origin and SOC at destination is substitutional. So when they start with low SOC, they are likely to choose a route to maintain high SOC level at destinations. For long distance evacuations cases, when charging is necessary, EV evacuees are more sensitive to queuing time compared to travel and charging time. We noticed that there is a strong preference to maintain desirable SOC at or even high levels SOC at destinations. And then the relationship between SOC at origin and SOC at destinations is complementary. So when they can start high SOC level, they also want to end with high SOC levels at destinations. From the evacuation attitudes, we noticed that non-EV owners still exhibit strong preference towards gasoline vehicles, maybe due to the concerns about EV specifications and charging accessibility, while EV owners demonstrate more confidence, but still face hesitations, especially for the long-distance evacuations. That's all about my study. If you have any questions, I'm happy to answer. Thank you.
Great presentation. Thank you. Any question? So I have a question here. So you mentioned that about evacuation, but the type of disaster, maybe you mentioned, but I probably missed it. So the type of disaster that evacuate happens, what it is, and does it have impact on the findings of the research? It would be if it would be another disaster.
Yes. So in the survey, we did not consider the intensity of the hazard. We just see that there is an evacuation order and everyone needs to evacuate from a certain point.
Mhm.
Just put a laser pointer. So there is like kind of like origin and then like a dedicated designated destinations. And we not kind of like telling them what is the intensity of the hazard. And also in the modeling, we considers kind of like hazard scenarios in our networks, but we translate it into kind of like road blockage and also power outages in the charging stations. And I think we just translated the hazard intensity to the impact to the infrastructures and then run it and simulate it directly.
Great. So one question from audience, how do power outage and blocked roads impact EV routing differently in Chicago versus South Florida?
Mm, yes. We we're not in this work, we're not kind of like evaluate the impact of hazard to the EV evacuations. It was actually in our other work. But definitely it depends, but from our findings from previous from other works is that even the we translated the power outages to kind of like the operationals, whether a certain charging station open or not, and see the impact of it. But then in Chicago network is a very small network, it's about 25 miles. So even though with that, we noticed that some of EVs still able to evacuate with and without charging, but we noticed there's kind of like more and more stranded people that evacuate, especially in larger networks like South Florida.
And one more question. I don't think you collected such data, but I do wonder what EV evacuees would do if the charging points were so busy they couldn't charge or couldn't get sufficient charging time of the hazard arriving, or power outages meant no charging available.
Yeah, we did not do that, but definitely in the one of in the future's direction of this work is actually to kind of like understand more of the charging choices, because in here, we let me put it back here, because in here we kind of like it's not really showing here. In here we just telling them that there is like two stop of charging stations, but we not necessarily allow them to choose which position and how many they wants to stop. And I think those questions is might be interesting to answer in the futures.
Thank you. Thank you. So, next speaker, Jiahui Chen. The topic is vehicle to home charging can cut costs and greenhouse gas emissions.
Hi colleagues, my name is Xiaohui Chen. Today I'm presenting a work by me, my advisors, Professor Greg Killian, Professor Paris Vashnev. The title is Vehicle to Home Charging Cuts Drivers' Charging Costs and Greenhouse Gas Emissions Across the US. First, let's talk about background. Cars and homes are the easiest among sectors to decarbonize through electrification. But do EVs really cut greenhouse gas emissions? Here's a study that compares the life cycle greenhouse gas emissions of battery electric vehicles with gasoline-powered hybrid electric vehicles. We can see that not everywhere EVs can cut greenhouse gas emissions compared to an HEV. And one of the reasons for this is that the greenhouse gas emissions for charging are assessed with marginal emission factors of 2018, meaning we are assuming that the cars will charge electricity with today's electricity mix and fuel mix throughout its lifetime. However, the grid will decarbonize regardless of EV adoption. And how will this actually affect EV charging emissions? Residential electric loads have limited flexibility because load following electricity is very hard to decarbonize. And changing the way that people consume electricity at home will more or less come with discomfort. And this is where EVs come in. Can we use EVs to shift around actual household electricity consumption without people changing their electricity consumption behavior? Furthermore, are there synergies between home and vehicle electrification? Home electrification such as a heat pump upgrade. For the household to utilize the EV battery for flexibility and for load shifting, we hear model 2 charging optimization scenarios and 1 default charging scenario. The default charging scenario is called uncontrolled. It is where state of charge drops by 40% consecutively, and the driver will charge up the battery up to 80% at the next slow charging availability. And for control charging, we're assuming there's an load aggregator where there's an intermediary that is exposed to market price, real-time market price of locational marginal prices. And the intermediary will optimize the charging behavior without compromising user needs, such as driving needs, to shift charging from expensive hours to cheap hours. And for vehicle to home, it takes 1 step further. It also optimizes the charging cost, but it can supply the home electricity consumption with the electricity stored in the battery by discharging energy back to the home when electricity prices are high, and charge energy back when electricity prices are lower. In order to do this, we first construct driving profiles based on daily driving records extracted from NHTS travel dataset, and then we simulate the EV energy consumption based on these driving events with the EPA rated fuel economy data. And then when we have the availability, the location, and also the charging needs of these vehicles, we can simulate how they charge and optimize how they charge in the case of control charging and vehicle to home. We assume the algorithm has 20 days of perfect foresight of the driving needs, the electricity system operation, and also the home electricity consumption, so that it can take advantage of the price difference between our different hours of charging, and then move around loads in order to lower the household electricity bills. And because vehicles home obviously would increase the battery cycling, it becomes a natural concern whether vehicles home can put too much stress on battery lifetime. And then in order for a safe check, for the sake of a safety check, we implement a degradation analysis based using NRail's blast light model. We assess battery capacity loss with calendar and cycling aging to estimate the impact on different charging strategies on battery lives. And for lifetime impact assessment, we assess both lifetime charging costs and the life cycle greenhouse gas emissions. The fuel cycle emissions, we use NREL's Cambium for marginal emission factors, and for the vehicle cycle, we use Argonne's GREET model. The lifetime assumed is a 15-year lifetime. We model 3 scenario years, 2024, 2030, and 2040. Between the 3 years, the grid decarbonizes and generally has more hours with cheap electricity generators on the margin. And to optimize and also assess the charging cost, we use locational marginal prices plus an adder to reflect the differences between locational marginal prices and the retail in real life. Then let's look at results. First, the cost. Down below is a figure of lifetime charging costs across different charging scenarios for each location in the contiguous US. The deeper the red is, the higher the cost. And here you can see blue. The deeper the blue means the lower the cost. And the reason why you see cost below zero is that in some places, vehicle to home reduces so much cost that it completely wipes out the charging cost, and also reduces some of the electricity bills that's incurred from other household electricity consumption. In this slide, we can see that vehicle to home cuts charging costs relative to uncontrolled and controlled charging substantially. We look at the left, the 2 boxes on the left, we see controlled charging versus uncontrolled charging. There's an improvement, and from controlled charging to vehicle to home, there's even more substantial improvement. And on the third box, we see that vehicle to home performs better when it comes to cost reduction in homes with heat pump than homes without heat pump, like baseline homes with the currently most popular space heating method. And this can also be seen on the right side. The box for baseline homes are showing not as great the cost reduction as for heat pump homes. As for emissions, controlled charging EVs emit lower life cycle greenhouse gas than HEVs everywhere in the US, and also, of course, than in her ICEVs. Moreover, if you look at the vehicle to home, there are even more places where the emission reduction is so high that it wipes out entirely the charging emissions and also the vehicle cycle emissions, meaning the upstream emissions from vehicle manufacture and the downstream end-of-life disposal. Meaning EVs can have net negative life cycle greenhouse gas emissions in some parts of the US. Here, if you look at the comparison between scenarios, similar to cost, we also observe similar improvement, changing from uncontrolled charging to controlled charging, and from controlled charging to vehicle to home. Now, we can observe similar synergy here between house electrification and having an EV. In homes with electric heat pumps, there is more emission reduction that can be achieved by vehicle to home, than in baseline homes. Then, if we look at the equivalent full cycles, in other words, the battery cycling from vehicle to home operations, we see that the battery cycling for vehicle to home exclusively is almost as much as for driving, and thus almost doubling battery cycles compared with uncontrolled charging and controlled charging. We will consider a case where vehicle to home discharging is restricted, because this scenario design stems from real life, a pilot program in the real world. Ford has a F-150 pilot program where trucks can power homes for like 2 hours a day through all the months, and drivers can be compensated for that. We also model a case in which vehicle to home can only discharge back to home during peak hours, and the discharging power is limited to 5 kilowatt rather than 10 kilowatt in our base case. The restrictions cut vehicle to home cycles to like 30% of the driving cycles, rather than almost as much as many driving cycles. Having looked at the cycles, we examine how the discharging constraints impact cost reduction and emission reduction. Here, the 4 figures are comparison between the constrained vehicle to home with controlled charging and this vehicle to home without constraints. We can see that though vehicle to home underperforms with the constraint than without constraint, which is natural, it is still much better than controlled charging. Besides applying constraints to vehicle to home discharging, we also assess the actual battery degradation effects from changing battery charging strategies. We exhibit here the second worst degradation change resulting from charging strategy change in each location, and the worst degradation increase we observed are among changing from vehicle to home, changing from uncontrolled charging to vehicle to home, and those worst degradation are lower than 5 percentage points, which is a very small effect on battery health. However, we do acknowledge that we need more future research to confirm this conclusion. So far, we have been talking about optimizing charging based purely on charging cost. What if we include greenhouse gas externalities in charging optimization? For example, a very conservative $51 per ton carbon dioxide equivalent. In this comparison, we observe a 3-way tension among charging cost, greenhouse gas emissions, and battery cycles. If we define abatement cost of greenhouse gas emissions as the change of cost over the change of emissions, we can actually calculate the trade-off that we face for each charging strategies when we include greenhouse gas emission externalities in the optimization. For control charging, it has the lowest abatement cost, but for vehicle to home in baseline homes and in heat pump homes, we also observe very low abatement cost. However, including greenhouse gas externalities in the charging optimization does increase substantially the battery cycling. We see in the upper panel, it is the case where greenhouse gas externalities is not included in the optimization. And in the lower panel, it is included. We see how starkly we see very starkly how the annual equivalent full cycles of EV batteries are increased substantially just by including greenhouse gas externalities, thus coming in as the third piece of that three-way tension. If we want to capture the low abatement cost of greenhouse gas emission, we will see a substantial increase in the battery cycles. And whether this trade-off between the three components are worthwhile is worth future research interest. In conclusion, vehicle to home is a low-hanging fruit to cut EV charging emissions and costs. With controlled charging, EVs cut greenhouse gas emissions relative to HEVs and traditional ICEVs everywhere in the US. For vehicle to home, it completely eliminates charging greenhouse gas emissions and also cuts some of the residential electricity emissions. It can also slash EV charging costs if owners are exposed to locational marginal prices. For example, through a load aggregator that optimize and schedule all their charging and discharging operations. Furthermore, vehicle to home creates synergies between vehicle and heating electrification. Last but not least, the effects on battery capacity loss caused by vehicle to home are likely modest, but these needs more research to confirm. Thank you for listening.
Thank you. So let's move to the next speaker, Wencheng Bao, on electric vehicle charging station at risk from hazardous event and power outages, analytic and resilience implications.
Hey everyone, my name is Wencheng Bao. I'm currently the graduate student in University of Illinois Urbana-Champaign. For today, I'm going to present my work with my advisor, Dr. Kantu. The title is about the electric vehicle charging stations at risk from the hazardous event and the power outages. We will provide the analytics and resilience implications study about that. And so first, I'm going to introduce our motivations for this research. So we know the EV adoption is growing. So like, for example, the California leading at 24% market shares. The ML program is also have to give the approximate $5 billion to accept to helping to have more EV shares in the United States to making more and more EV in the market. And however, the one thing we need to focus on is the charging infrastructure faces unprecedented climate risk. The annual hazard damage have reached approximately $700 billion and rising, and with 2023 along the same 28 disaster caused nearly $95 billion in damage. So in this research, we are conducting the study to examine the relationship between the hazard severities and charging infrastructure vulnerabilities. And we want to investigate how natural disaster risk affects the strategic deployment of level 2 and the DC fast charging stations. We want to understand the connections, which is essential for building the resilient EV future that can withstand the charging climates. And first, we need to talking about how well the hazard will influence the charging stations. We will following the Johnson structures. Based on the Johnson structure, it have the first set. The first set is called the individual assessed risk, which is related like the hazard directly influence the charging stations. For example, like the wildfire, and the fire will damage the battery, destroy the charging stations. The second one is called network impact, where the disaster maybe reduce the transportation speed or will block the road. The people cannot get into the charging stations, cannot access it. The third one is the independent failures. which is, for example, like the power outage, the power grid. The charging station will not have the power supported, so it's unused. And the first one is social economic losses, where the public trust in EVs might be loose when the people cannot access reliable charging during the hazardous events. And the next, for this study, we have reviewed several data sets. I'm going to introduce the data set we used first. The first one is called the FEMA National Risk Index. This FEMA National Risk Index includes the matrix qualified the hazard risk levels for U.S. census tract, and it covers 18 different nature hazards. And for our research, we majority focus on the two index. The first one is FEMA risk index score, which is normalized value ranging from 0 to 100. And if for example, it's a value for each census tract is like the 98, 99, pretty high, which represents this area. It's more dangerous and easy to get economic losses from the natural hazard by different type of hazard. Another risk index we are talking about is called risk index ratings. The FEMA categorized in the 5 quantitative levels from the very low, relative moderate, relative high, and very high, based on the normalized FEMA risk index values. And by some statistic in the right over on the graph right over here, we have a plot in each census tract. What is the FEMA index score is looking like? If the color is more deep, that represents the value is more high. And we need to focus on for example, like there is a 2.85% of the census tract in the United States. Oops, sorry. Categorized as a very high risk, and we have focusing on the figure in the right over here. We can see that like the California, Florida, and Texas have the majority place have the very high census tract. It's rating in the very high FEMA risk index rating. And next data set we are talking about is the alternative fuels data centers. We're using this data center until July 2024, and we categorize in the census tract level. We find in the US there are 25.85% census tract have at least one charging stations, and we have plot right over here. The purple census tract represents the census tract have the both DCFC and charging station level 2. The green one is only for the DCFC, and the blue one is only for the level 2. On the right-hand side, we provided some equity Lorentz curve calculations. So it is we have plotted the level 2 and DCFC ports across the US census tract categorized by different risk level. The horizontal axis represents the cumulative share of the population across the census tract, while the vertical axis represents the cumulative share of the charging ports. And we can find from the purple line, it's very high, and the orange line is very low. So we using the FEMA index and calculate with that. And we separate like this graph is for DCFC, this graph is for level 2. And for the DCFC, only for the census tract be labeled as a very high risk area. We found the bottom 60% of census tract, there is no DCFC, and they have the highly concentrated in the top 20% of census tract have the 80% of DCFC. And for the level 2 ports, from the very high risk area, the bottom 60% of census tract only have the 10% charging station can be used, and for the top 20% of the census tract populations, they have the 70% of the level 2 charging stations. And since we have the census tract, the number of the risk score, we know from the alternative fuel center, we know how many charging station to level 2, how many DCFC, how many ports about it. We can calculate the correlations and the p-values, and we have present result over here. So we find overall we find the weak but statistically significant correlations between the distribution of chargers and the national risk index score. So if you're checking like the level 2, the correlations it's lower than 0.1, and the DCFC it's just excess 0.1, but also it's below the 0.15. But the significant the level, the p-value, it shows the significance. The p-value is smaller than the 0.01. And next, after we review the risk score, we review the charging stations, we next go into the power outage dataset. We're using the dataset from US DOE Office of Electricity, and this dataset provides the detailed information on date, locations, type of incident, and the entities involved. So in 2023, there are totally 348 power outage defined. And if we going to see the line curve right over here, we can find the majority reason to cause the power outages is a weather or natural disaster or the severe weathers, which is two majority reasons. And by these two reasons, the influence charging level 2 and the DCFC ports is dominantly. And if we by checking, because we know the locations where the power outage happens, by checking which state is have the most power outage in the 2023, we find that Texas have the largest power outage event, and also have the most charging stations be influenced by those kind of the power outages event. Therefore, we're moving to the study in the case study in Texas. So from the Texas, we know that they have 325 the census tract be labeled in the very high, and more than 1,000 be labeled as the relative high dangers. And the mean value for the risk score is 6.65. It's much more than the 50 US mean. And for the level 2, the port, they have the approximate 5,000 ports, and DCFC also have the 1,600 ports. And we then also provided the algorithms calculations right over here. We provide like the level 2 and DCFC ports across the US census tract. We have this distribution curve across the Texas counties categorized by the power outages frequency and durations. The horizontal axis represents the cumulative share of the power outage frequency and durations, while the vertical axis represents the cumulative share of the charging ports in the Texas counties levels. So overall, we find the ugly stuff is be labeled right over here. We find that 70% of the level 2 stations are in the top 20% of the counties, and for the DCFC, 45% of the stations are in the top 30% of the counties by cumulative power outage frequency and the durations. And after that, we provide the really detail of the curve right over here. It's so in this diagram, if we check each county's colors, if the color is more deep, that represents this place have the more charging stations, and the bar, if you're seeing each small blocks, probably they have the two bars that represent the frequency of the power outage is 2, and the power outage durations, it depends on the bar length and the colors. So in majority from this table, we find the majority power outages happen is around the Dallas and the Tarrant counties, and the longest power outage is 152 hours. This is happened when at the beginning of the 2023, because with the cold wave. I have showed some the basic statistic right over here. And although we know the winter weather and cold wave have the significant risk factors across the Texas, but not only this, there are also some other risk factors in Texas, also in relative high or very high risk zone. And for example, if you're checking in this corner of the Texas, there are also some power outages happen. This means only consider the winter weather, and the cold wave is insufficient, and we need to consider the multi-risk visualize the charging ports, number of the power outages during of the power outage, and some place of the risk index when people is considering to have the more when the policymaker or to have the more access to helping people to process the power outages. And then if we consider for all of the decision makers, there is only limited budget of their disposals. Maybe they need to prioritize which regions need to process first, have the immediate interventions. So then our study using the Texas example to develop into the relationship between the risk index score and the duration of the power outage. we pinpoint the crucial threshold. This threshold marks the risk index score at which target investment in regional charging infrastructure becomes essential to ensure the reliability and resilience. And by addressing this threshold, we aim to safeguard the continuous operations of electric mobility in the high-risk areas. So from our calculations, by using the KS test at the 95 confidence level, we find the threshold. This number is 97.18, and we also do the regression discontinuity design to making sure the regression trend below and above the 97.18 is different. It is significantly different. And overall, we can see that maybe the policymaker can focus on the county or census tract, the threshold score over the 97.18 in first for if they have the limited budget. So overall, in this studies, we have find some interesting stuff. We for the hazard sustainabilities, we find the weak but statistically significant correlations existing the FEMA risk scores and the distribution of the level 2 ports and DCFC ports. And for the behavioral outage and the impact in our case study in the Texas, we find when the risk score over the 97.18, the likelihood of the outages increased significantly. And for the infrastructure disparities, we have mentioned like maybe the high risk census tract tend to host a large share of the level 2 stations, while DCFC stations are more evenly distributed based on our Lawrence curve calculations. And for some future considerations, probably the policymakers and the researchers should account for hybrid hazard and power outages when planning charging infrastructures. And here is some reference, and thanks for listening to these presentations, and feel free to ask any questions if you have.
Thank you, Wencheng, for great presentation. Next speaker is John Helveston. The topic is the spatial patterns of electric vehicle accessibility in the United States.
Right. So, okay, folks, this talk is motivated by this idea, innovation needs paradox. Some people might have heard of this, which is this idea that people who can often benefit the most from a technology are often the last ones to adopt it, often because of cost. In the case of electric vehicles, EVs are much cheaper to run, they have lower operating costs, they're less polluting, there's a lot of benefits to them, but primarily they're adopted by the wealthiest people right now because they're so expensive. And so this study is really trying to get at accessibility, both in terms of affordability to some extent, but also just physical accessibility. Where are the cars and can you actually get access to them? So the study is very descriptive. There's zero modeling at all. We're just looking at data, exploring it, and understanding the sort of status of the market and how it's evolved. The data set is a very large data set from marketcheck.com. They go out and web scrape every dealership in the country, and we get records of all of their online listings. So we have about 105 million vehicle listings from 60,000 dealerships between 2016 and 2024. So those tables just sort of summarize the amount of listings. I mean, by far, the majority of the cars are conventional vehicles. That's a CV, gas cars. But we have hybrids, plug-in hybrids, and battery electrics that we look at as well. This study is really focused on PEVs, so these two groups, right? We collectively just look at plug-in hybrids and battery electrics together as a PEV. So first question, how many dealers are even carrying them? And how has that evolved over time? So very basic summary charts here, but this is sort of a positive story. It's looking much better than it used to even a few years ago. So nationally, if you look at the left side, that's the new market. We're about in 4 out of 5 dealerships now have at least one electric vehicle for sale. That is up from, the opposite of that, about 20% back in 2016. Each line here is a state in the US, so you can sort of see the variation across the different states. So most states are now up here in this 80% territory. We have outliers like California and Hawaii, but even the states at the low end of the spectrum are still over 50%. In the used market, it's flatter, it's growing, but not near as steeply, which makes sense. It takes time for those cars to diffuse into the used market. But we are seeing, a positive trend. Now, that's just saying that there's more dealers that carry EVs. It doesn't tell you about how many cars are actually there when you get to the dealer. And that's what this next plot is. This one is a lot more depressing. Even in the new market today, nationally, we're very much in single-digit territory still. So only about 7% of listings at dealerships nationwide are plug-in vehicles. So over 90% are still conventional or hybrid vehicles. Now, again, outliers of Colorado and California are really shooting up here. 1 in 4 cars in Colorado that are new listed are electrics, but nationally, it's quite low and much, much lower in the used market as well. Only 4% of used used vehicles are EVs. So we're basically seeing more EVs available spatially. There's more dealers that have them, but when you get to them, they might only have, 1 or 2. There's just not a lot of options at each dealership. Affordability, though, is, I think, the biggest concern here. So when we look at that same y-axis here, what is the percentage of listings that are electric? Note here that we only get up to 30% on this chart. I have now bin this up nationally by price buckets, right, in increments of $20,000. And these circles down here are telling you the overall size. This is just 2024, but it's about the same every year. So you can see where the size of the market is and where the growth is. All right, so all the growth has really been in the very, very high luxury segments, to the extent that we're now at 1 in 3 luxury cars are electric, which is good. That's not a bad thing, but that market is extremely small. So we've seen a lot of rapid growth in EV adoption, but this is telling us that we can expect that adoption to not continue quite as rapidly because the vast majority of the market is down here in these sort of sub $40,000 range, and we have very, very few offerings in those price segments. So affordability is still a major challenge. There's just not cars for sale in those price ranges where most people buy their cars. There's just not electric vehicles, not many for sale. So that's just some basic, summary stats of this large data set. The majority of this study, though, was to look at, spatial access. Where are these EVs and how hard is it to get to one? And here we're not even thinking necessarily about buying them, but really about the experience of going to test drive or see the EV. And so we think it's really important that you have good access to be able to go test one out. So the way we did this was we created this vehicle accessibility metric where we took the census tract centroid. So right in the middle of every single census tract, that's this little black line in this example. There are about 70,000 census tracts across the US, so they're pretty small areas. And then we found the driving route to the nearest dealerships. So in this little diagram, this is sort of a cartoon example, but we have 2 dealers. This one's closer. The little dots here are telling us the type of car. So the first EV closest to this census tract would be this travel time A, to get to this dealer. If you wanted to get to the second or third EV, though, you'd have to go out to this one because they only have 1 EV here. This one, they have 2. All right, so it would be time B. And likewise for the conventional vehicles, the first 2 would be this time, the third would be this. So this is how we calculated these times. We use this open source routing machine to get all of these different pairs to every single dealership at every single centroid. So we're talking many millions of trips calculated here. And so we're ultimately looking at the travel times, right? How long do you got to drive to get to that car? And all of the results I'm going to be showing you are in measures of that time. And what we actually show you is the time to the 10th vehicle out, not the very first one. And we do that because we're looking in periods of years, and cars are often listed online for maybe a month. And so it's not really fair if you say, well, this one car was really close by, but it was only there for 3 weeks in July. The rest of the year, the next closest car might be 20 miles away. And so it's really unfair to say the first closest car is really a good representation of access. So we use the 10th one out. That gives us more access, like more sort of temporal coverage as well. So in the record of all the records that we see in 1 year, give us the 10th closest one. And that's what we're looking at. So this one chart summarizes the whole country. So with all those census tracts, we aggregate them up based on the population of how many people live in those census tracts. And now we're able to construct this CDF of the percentage of the population and how far they have to go to get to that 10th vehicle. So the black curve is conventional vehicles. This is gas cars. This is the status quo. And 80% of the population, that's just this, if you sort of go across this horizontal here, they can get to a gas car in 12 minutes, which is kind of crazy. I mean, most people on this call, you probably have a gas car for sale within a 12-minute drive of where you live. And you can see that the EV market is evolved quite a lot. Back in 2016, that was an hour. You know, to reach 80% of the people, you were at an hour of driving time. That's down to 22 minutes today. So that curve is starting to collapse towards conventional vehicles, and that's an indication of that more dealers are carrying these EVs, right? So that first chart I showed you, that we have more and more dealers that have them, but they don't have many available at those dealers. So this is getting better. I mean, our geographic spatial access is improving. But then we also look at disparities. So we take the same idea, the same CDF curve, and we look at it within subgroups, subsets of the population. So we collect together different census tracts that have the same, let's say, price segment or their urbanicity. So urban versus rural, income brackets, and as well as we even look at political. So their political voting from the 2020 election. And we do see some pretty big differences now in accessibility. Note here that this is the additional travel time. So now what we're doing is, instead of comparing to the gas cars, we're just taking the subtraction of, subtracting away the gas car and how much more time do you have to go to get to the nearest EV beyond the nearest gas car. It just makes it easier to compare multiple categories. So what we find is, low-income areas have more travel time to cover, although this is not as severe for most of the population. That's these curves. Only really once you get above this 80% do we see some pretty big differences. Rural areas have a big gap between urban, this is this black curve, which has very, very high access, and most people within 10 minutes, compared to the red curve, which is rural. And then Republican strongholds are actually the single biggest disparity was in political disparities, where places that are Democratic strongholds have very high access to EVs. Republican strongholds have very, very low access. And so these things are probably correlated, right? Rural and Republican Democrat voting is correlated. Income can be correlated with this as well, but we're just sort of showing you these disparities all at once to show you that access is not the same everywhere in the country. And then geographically, if you just want to look at this spatially, these are those same 4 bins that I showed earlier in increments of $20,000. And you can see that there are some places that are essentially deserts. They're just places that you cannot find an EV, at least within that price bin. It's particularly bad at the low end, right? So this is also just because there's so few EVs that are priced in that segment. So this is inclusive of new and used cars combined. We just put them together and said, is there any car, whether it's new or used, but if it's in that price range, put it on here. And so the dark colors are, an hour or more, maybe an hour and a half of driving till you get to the nearest EV. It's much better in these higher end segments, right? But there are some places that are pretty persistent. You see some of these gaps in the South. They're sort of persistent in most of these places. The Midwest has lots of gaps. So there are places where it's just going to be very hard for you to find and experience an EV. Okay, so some findings to just sort of summarize what this exploration kind of shows us. Things that we already know. We know EV accessibility is spatially concentrated. That matches with EV adoption, right? We've already seen adoption is spatially concentrated as well. So, this is somewhat of a proxy of demand, right? Dealers are not necessarily going to stock cars if they don't think they can sell them locally. But that means there's going to be this big divide between especially urban and rural. And so we're going to have, a need for targeted grid investments in places that are very urban or places that have high income areas. You're going to have peak demand challenges there much more than you will in rural areas. Unfortunately, this probably also means there's going to be some missed opportunities. The rural areas of the country are some of the best for wind resources in particular, and things like what we've seen a lot of today, people presenting about smart charging and things like this. We may not actually be able to leverage a lot of that in some of those places if there's not a lot of adoption there. So that's just one particular implication for energy. The affordability gap, I think, is one of the biggest things I want to highlight. So under $40,000 in the new market, only 1.3% of new vehicles for sale are EVs. All right, so the vast majority of new cars are over 40K. and 94% of the used market is under 40K. So almost every used car is under that price range, and there's very, very few EVs. So really, we have a lot of this. We have a lot of EV makers making these super high-end luxury cars that are very expensive. We need a whole lot more cars like this. Obviously, this is like not even an EV. This is just an AI generated image. But it'd be great if we had like a $10,000 EV that was something of a clunker, maybe 10 years old, but it still ran. You basically just have zero options for that right now. You have to buy a gas car if that's your price range, and that is the price range for a lot of people. And then finally, dealerships really matter. Even though I said, this is probably a lot of the results are proxies of demand. But what that translates to is a lot less exposure, right? So if you live in a place that is sort of one of these deserts or has very low access, you may be EV curious, right? You might be interested in them, or you might just want to try it, but you basically can't. I mean, not without a pretty significant inconvenience. And you're surrounded by, abundant conventional vehicles nearby for sale. So if you're looking to experience an EV just to learn about it, that's going to be really hard for those places, which is probably going to just exacerbate these disparities, right? Places are not going to have experience, which means they're not going to be as convinced that this is a good tech for them. And you end up again with dealers saying, okay, well, then we're not going to stock them because no one's going to buy them. And this cycle here of lack of exposure leads to less demand, which leads to less exposure. And we know that exposure and direct experience is really important. If you get in an EV and you test drive it, that's a huge factor in convincing people to consider it. So that's all I have. If you want to check out these slides, you can go to this link and check it out. My slides are just a website. So that's it. All right. Thank you.
Thank you, John, for the great presentation. So any question from the audience?
I have one question from John.
Sure, go ahead.
Yeah, thank you, John. Great presentation. Somehow going back to your first slide, research motivation, I was wondering, how do you define the group of people who need this type of vehicles?
You mean this innovation needs paradox thing?
Yeah. I mean, I was thinking maybe considering vehicle ownership could help in this analysis. Do you think that could help?
I mean, that was just more of a framing idea to say that this is sort of, I think, well known in vehicle ownership in general, that lower income households in particular can really only afford cars that are often outdated, like that have outdated tech, which means they're going to be less efficient, which means you spend more of your money on operating costs, like paying for gas. Whereas if you had an electric car in their hands, that would really help them. They would not be spending so much on fuel every month. But they just can't get to that car because it's too expensive. Right? So the upfront cost is still a major problem. So that's kind of what I meant by that, was some of the households that could benefit the most if they could actually afford one of these cars are low income households, but they often cannot because the prices are just too high.
Thank you.
Yeah. And I see one here. Do you have recommendations for how to increase EV access? Yeah, import Chinese cars. But no one wants to do that here in this country. We have 100% tariffs on the most affordable cars in the world, and we keep them all out. I think we would see a very different market if we had competition from abroad of really good and affordable cars, but we're not going to see that, at least for next 3 years. Yes, we talked about that in the study too. Someone made this question about direct access. Direct to consumers would be, I think, a really good thing to continue promoting. Just allowing people to buy the car if they want. That's sort of the Tesla model. A lot of states don't allow that. A lot of states require dealerships and things, and that causes barriers to entry. And it also creates some of these barriers to adoption potentially, where dealers just are unwilling to stock them. Of course, the challenge with that is you have to already know you're kind of ready to make the purchase. So if you're already ready to make a purchase, direct access may not be super helpful. What we really need is places for people to test drive these things. We need like ride and drive experiences. We need places where people can go out and try the car. And the dealer is usually the number one place to do that. So if it's not going to be the dealer, I don't know who else. But I think, you know, promoting things through direct experience is really, like, I think a key thing that's lacking right now.
Thank you. So one
Okay.
last question, since we have like 2 minutes.
Yeah.
So how do you think the Big Beautiful Bill would affect the findings in your study? Do you think that it's gonna impact the access or just increase the prices we would expect?
Both. I mean, we're going to not see as much growth as we would have otherwise. I mean, without a doubt, the IRA incentives were working. Definitely would have seen more demand, more production of EVs. So we're going to see less of all of that under that bill. And the prices of everything is going up because we have massive tariffs on all input goods. So all cars are going to be more expensive, and especially EVs. Sadly, this is the reality.
Thank you. Oh, one more question.
They're lower the operating costs are certainly lower when you just compare the fuel, right? Not necessarily maintenance. The biggest uncertainty is that maintenance and insurance has gone up. Why is that? Because these cars cost $70,000. So if there have been people who've studied like the repair cost of an EV, and they're finding that they're much higher than gas cars. That's because you're repairing a luxury car. If there were actual affordable EVs in the market, you'd probably find that their repair costs aren't so high. A Rivian panel, when you get like a ding on the panel of a Rivian, it's like $20,000. So it's not a good situation.
Great, thank you.
Yep,
Nice
thanks.
discussion. So last speaker would be Fatima Ahmadipour from University of Colorado, Denver. She would speak about measuring the impact of e-bike rebates on travel behavior.
Hello, everyone, and thank you for joining. My name is Fatima Ahmadipour. I'm excited to present our research titled Measuring the Impact of e-bike rebate on travel behavior. This work is a collaborative effort with my co-authors. This is a quick overview of what we will need to cover today. I'll start with an introduction to the study, including some background on e-bike and Denver's e-bike rebate program and the key research question we set out to answer. Next, I'll walk through the methodology, including a summary of the data we used and the model specification. Then I'll present the results, highlighting both the estimation findings and the key takeaways from the analysis. And finally, I'll wrap up with some limitations of the study and suggestion for future research directions. So let's start with why e-bike matters. They can significantly reduce barriers to cycling by helping people ride more often and over longer distances. E-bikes are especially useful for replacing short car trips, but cost remain a major hurdle for many people. That's why incentives like rebate program are so important. They help make e-bike more affordable and accessible to a broader population. In early 2020, Denver's Office of Climate Action, Sustainability and Resilience, in collaboration with the city's climate action task force, set out to identify projects to support the city's climate goal. They recognize e-bike are a cost-effective way to reduce car trips and lower emissions. As a result, they launched the 2022 e-bike voucher program with $250,000 from the Climate Protection Fund. The city partnered with 9 local bike shops and a contractor to provide point-of-sale discounts, which was up to $1,400. By the end of year, they had distributed over 4,400 vouchers, with nearly half going to income-qualified participants. This study is based on that program and a survey the city conducted to evaluate its effectiveness. They generously shared the data with us, and we use it to model key outcomes and answer our research questions. These four research questions guided our study of Denver's e-bike rebate program. First, we want to know who benefits from the rebate in terms of e-bike ownership. And then we look at whether the rebate led to a modal shift and which modes were replaced, and by how much. Next, we explore which socio-demographic groups replaced the most vehicle trips. These slides show overall e-bike usage pattern. The top chart highlights peak usage during common commute hours, around 8 to 9 a.m. and 6 to 5 p.m., suggesting many are using e-bike for work or school trips. The bottom chart shows a steady usage across all days, indicating regular everyday use. This table gives an overview of our survey sample. There is a lot of information here, so I'll just highlight a few key points. Most respondents were between 31 and 40 years old, male, white, and reported higher income. But there are two important things I want to draw your attention to. First, over half of the respondents said they wouldn't have purchased an e-bike without the rebate. And second, after getting the e-bike, 71% reported that they drove less. Excuse me. This table gives an overview of our survey sample. Excuse me. We conducted some cross-tab analysis and found interesting pattern. Age and income showed the most variation in driving behavior. Adult aged 31 to 50 and those earning 25 to 50K were more likely to reduce their use of private gas-powered vehicle. This suggests that rebate had a stronger impact on reducing gas-powered vehicle trips among lower income and middle-aged recipients. We used two types of probit model in this study. The binary probit model is used when the outcome has two categories. For example, someone reduced car use. The order probit model is used when the outcome has ranked categories, such as using a car more, about the same, or less often than before. The formulation for the binary probit model is shown above, and the order probit model is shown below. Both models estimate probabilities based on explanatory variable and assume normally distributed errors. This is just a general overview. To see who really benefit from the rebate, we asked people if they would have bought an e-bike without the rebate program. Four groups stood out as more likely to buy one anyway. Older adults over 50 higher income individual, women, and people who had already used a shared e-bike or a scooter. And also we looked at how e-bikes replace other modes, especially private gas-powered vehicle, transit, and traditional bikes, and what influences that shift. After getting an e-bike, 71% of people said they drove less. Our binary model showed that people earning between $50,000 to $75,000, as well as those over 50, were less likely to reduce driving. On the other hand, men and former transit users were more likely to cut back on private gas-powered vehicle usage. And the people who would not have bought the e-bike without rebate are low income and men. At the same time, the people who reported lowering car usage are the low income and men. So the rebate actually contributed to providing the e-bike to low income people, thereby reducing car trips on the road. Older adults were more likely to purchase an e-bike without the rebate, likely due to their mobility needs. Women were also more likely to purchase an e-bike, possibly because e-bike help reduce common barrier to cycling. However, they were less likely to reduce their use of gas-powered vehicles, likely due to trip purpose such as shopping or transporting children, which may be less practical by e-bike. Why, excuse me, can you go to the last slide? Thank you. While higher income individual above $50K were more likely to purchase any bike, those earning 50 to 75K were less likely to reduce car use compared to individual earning under $25,000. This aligned with prior research showing that e-bikes are especially effective at replacing car trips among lower income individuals who often rely on them for essential trips like commuting. In contrast, middle income users tend to use e-bike more casually, and higher income users often adopt them for leisure or convenience. The marginal effect plot, excuse me, can you go to, thank you. The marginal effect plot show that adults age 50 and over were the least likely to reduce car use, and age had the strongest negative impact on driving behavior. We look at what drives change in transit use after getting an e-bike. Both frequent and infrequent walkers were more likely to reduce transit use, likely because e-bike offered either a faster or more convenient alternative. Higher income individuals who earn over $50,000 were less likely to cut back on transit. People who were willing to buy an e-bike without a rebate and those who previously used share e-bike or a scooter were also more likely to reduce their transit trips. Also, after getting an e-bike, nearly half of the respondents rode their traditional bike less. Our model shows that men and people with higher income, above 100K, were less likely to cut back on traditional biking. On the other hand, those who use transit often were more likely to reduce their regular bike use. Even frequent cyclists show a slight drop. High-income users show a smaller reduction in traditional bike use than low-income users because they use bike for leisure activities. Men were more likely than women to continue to use traditional bike more. Additionally, those who previously used shared micromobility option were more likely to reduce both car and transit use after getting an e-bike. These findings highlight that prior exposure to e-micromobility and existing travel habits play a key role in supporting lasting shift towards more sustainable transportation choice. This study had several limitations. The models explained only a small share of variation in behavior change, indicating the need for additional variables, particularly the variables related to trip purpose. The analysis relied on self-reported data. Income was reported without household size, and the sample lacked demographic diversity, limiting deeper analysis. Additionally, many rebate vouchers went unredeemed for unknown reasons. Future research should explore non-redemption factors, use passive data to track behavior change, and include interviews to assess equity and program impact more truly. Thank you so much for your attention. If you have any question, this is my email address.
Thank you, Fatima. We have time for one question. So there is one question from audience. How did you obtain your data specifically about the e-bike trips? E-bike trip used by time of day?
We use the data that was collected by, City and County of Delaware, and these updates are available in the websites.
Thank you. I hope that your question is answered, Paulina. This was it. So any more question? So if not, thank you all for attending this presentations and hope you have a great rest of the day. Thank you.